Good afternoon and welcome to your science review with Mr. Blade. Today we'll be working an example using a position versus time graph. Now I've already drawn one up over here, but this is an example of a position versus time graph. Sometimes you'll see it referred to as a PVT graph. Now what we're going to use this for is we are going to solve for the velocity and do some other things to describe the motion that is described in this graph. Now what you will see here is that x is our position and we have it plotted on the y-axis. Our time, measured in seconds, is plotted along the x-axis. Now this may be a little confusing for some, but just remember that position is measured with an x and is on the y-axis in this case. Now some things that we know about the motion of this object just based on the graph itself are as follows. We can see that this line is straight. That means it moves at a constant velocity through this time period. Next, we also see that it is becoming more and more positive, which means that this object is moving away from its origin point. Now let's go ahead and start solving for the velocity of this object. Now, one way to define velocity is equal to the change in our position divided by the change in our time. Okay, now you may have noticed I'm using a new symbol. It looks like a triangle, but it's actually the Greek or Roman, I don't know, letter delta. It is a capital letter delta, and it's the precursor of our letter D. All right, so we have delta x over delta t, which again can be read as the change in x over the change in time. Now, we calculate delta x and delta t by doing x2 minus x1 divided by t2 divided by t1. Okay, our final x minus our initial x divided by our final time minus our initial time. So let's go ahead and plug in the numbers that we have over here on our graph. We have 15 minus 3 divided by 8 minus 0. Now, you'll also notice that our x is measured in meters and our time is measured in seconds. So when we do our math, we will see that 12 divided by 8 is equal to 1.5 m divided by s. 1.5 meters per second. Okay? Now, if you went through algebra, you probably already noticed that what we just did was calculate the slope of this line. That is true about all position versus time graphs. The slope of your position versus time graph is equal to your velocity. So if you remember how to calculate slope, you know how to calculate velocity. Okay, let's continue by doing another example. So take a look. I have redrawn my position versus time graph to include a few key changes. Now, we still have a straight line, which means that we are still following a constant velocity. But you'll notice that this line is pointing down now. For those of us out there who have already taken algebra, this means that the slope will be negative. Now, I include this because I want you to be able to check your own work by knowing some things about your answer before you start the math, okay? So we know this slope should be negative. So if we do the math and get a positive slope, we know we did something wrong. So let's go ahead and do this math now. We already said that our velocity is equal to v equals delta x over delta t. Okay? And again, we will remember from a couple of seconds ago that delta x equals x2 minus x1 and delta t equals t2 minus t1. Okay, so let's plug in our numbers from our graph. And in this case, our x1 is 18 and our x2 is 6. So 6 minus 18 divided by 12 minus 0. Okay? We follow that to our logical conclusion and we have negative 12 divided by 12. And let's not forget to include our units, m divided by s. So negative 12 divided by 12 is equal to negative 1 meter per second. Likewise, this conforms to what we already expected to see. We expected to see a constant slope here, and we expected that slope to be negative. Both of those things turned out to be true, so we can be reasonably sure that this is the right answer. Okay? So, thank you very much. I hope this was helpful, and see you in class.